Welcome back to Calculus 1. In this lecture, this is our third and final part of our topic of derivatives and the shape of a graph. Parts 1 and 2 introduced first derivative ideas, increasing, decreasing, and second derivative ideas related to concavity. In this third part, we're going to pull it all together and deal with curve sketching. Okay, so before we get started with this lecture, make sure you feel completely comfortable with the content of part 1 and part 2. The most important part from that, we're going to be making sign charts for the first and second derivative again. And if you feel a little uncomfortable with that, that's likely to manifest itself here when we get to curve sketching. The approach I like to take basically relies upon having those sign charts already. Once we have those, curve sketching will be a piece of cake. So again, make sure you're completely comfortable on parts 1 and parts 2. Definitely go back and review those before diving into this lecture. Okay, with that in mind, let's go forward. So we have from our first derivative, the idea that it tells us about the function being increasing or decreasing. And the second derivative of a function tells us the concavity of the function, the curvature, whether it's curved up or curved down. Now, a very simple approach to curve sketching, which has a lot of steps that go into it, but each step is something that we've already have done, kind of comes from what I like to introduce and call the 4 basic arcs, or 4 basic shapes. And these are going to be what come from the signs of the first and second derivatives. Now, the 4 arcs are right here. When we actually use these to sketch a graph, these arcs might be stretched, compressed, horizontally or vertically, but for the most part, every graph can be built out of a combination of these shapes. It might seem rather surprising, but these 4 arcs are going to be the foundation for curve sketching. Now, what I'd like you to do is give yourself some time for a very brief exercise, but albeit extremely important in my opinion. What I'd like you to do is label each of these 4 arcs with 2 signs. Label them with a sign for the first derivative, whether or not the function or arc is increasing or decreasing, and then a second sign for the concavity from the second derivative, whether it's concave up or concave down. Write them in the order. The first sign will be the sign of the first derivative, second sign would be the sign of the second derivative. And you should end up with 4 possible sign combinations: positive, 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 negative, negative, positive, and positive, positive. So pause the video and give yourself an attempt at labeling all 4 of these arcs with the 2 sign combinations for the first and second derivative. We'll check in a little bit. Welcome back. Let's go ahead and take a look at these sign combinations. You should have them, if they were correct, in this order: plus, minus, 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 plus, plus, plus. Okay, and again, those signs refer to the sign of the first derivative and the sign of the second derivative. So just to make sure you see where they come from, let's go left to right with the arcs. The first arc there, as you move left to right, is increasing, and that arc is concave down. Increasing corresponds to a positive first derivative. Concave down refers to a negative second derivative. So that's where we get this sign combination, plus minus, or positive negative, however you want to describe it. All right, the other ones in order are decreasing, concave down. So minus, minus for the 2 sign combination. The next one is decreasing in concave up, minus, plus. And then the last one is increasing and concave up, plus, plus. Now, how we actually tie this into what we covered in parts 1 and parts 2 of this lecture, that was where we introduced our sign charts for the first and second derivative. And once we have those 2 sign charts for each the first and second derivative, we can actually use that to determine the sines and get these 4 arcs. So once we have our sine charts, the 4 arcs basically fall into place if we have a kind of properly filled out sine chart for both first and second derivatives. All right, now while the 4 basic arcs I'll say are the foundation for curve sketching, as I'll take it in my approach, there's a lot of other features for graphs that you might have covered and introduced back in algebra and pre-calculus that we're going to need in order to deal with some technically complicated things that typically happen in this first course in the calc sequence. All right, one topic that it might have been last talked about in your pre-calc course, we need to keep in mind what the domain of our function is. All right, things to keep in mind would be possibly division by 0. That could make a function undefined. You would want to exclude any x values that lead to division by 0 and things of that nature. All right, back in algebra, you were introduced to x and y intercepts. We're going to still use those here. Recall for the x-intercept, we set y to 0 and then solve that equation or function equal to 0, and we solve for x. For the y-intercept, we set or plug in x equals 0 to our function. All right, and one thing to keep in mind, for the things we're sketching, functions, they have to pass the vertical line test. What that means is you can have multiple x-intercepts. You can't have multiple or more than one y-intercept. Otherwise, if you did, your graph would fail the vertical line test and not be a function. All right, back in your pre-calc course, you likely talked about even and odd functions, which are the technical way in a mathematics course we deal with symmetry in a graph. So you might recall if a function is even, f of negative x equals f of x. Plugging in a negative x value is the same thing as plugging in the positive value to the function. If that property is satisfied, the graph is symmetric over the y-axis. All right, and there's a related property, a function being odd, if f of negative x equals negative f of x. In other words, you plug in a negative to a function, and it's the same thing as taking the negative of just plugging in the positive x value. All right, and this leads to what's called symmetry through the origin, which is a twofold symmetry. The graph is simultaneously symmetric over the y-axis and x-axis together. Not all functions have these symmetries, but we can sometimes take some shortcuts if we see these symmetries in our function. All right, other features of some graphs, but not all, are horizontal and vertical asymptotes. Typically, we're going to look for rational functions or fractions. Those are going to have usually vertical and horizontal asymptotes. And also basic exponential functions like e to the x and e to the negative x. They don't have any vertical asymptotes, but e to the x and e to the negative x do have horizontal asymptotes in one direction, either towards infinity or negative infinity. All right, we can usually find the vertical asymptotes of a function by seeing where the function becomes undefined. Usually, for most simple functions, that's as simple as seeing where the denominator becomes 0. And to find horizontal asymptotes, this is where in calculus, we use the idea of checking a limit at infinity as x approaches positive infinity or x approaches negative infinity. Some functions have different asymptotes in different directions, but not all. All right, and then the last part is what we most recently covered, the information from the first and second derivative. What we're going to be using from that are critical points, the possible inflection points. Those lead into the sine charts. In order for us to actually sketch a graph, we've usually been finding the critical points and possible inflection points as just x values or x coordinates. We would also want the corresponding y coordinates for any and all critical points and possible inflection points. And you can just plug those x values back into your original function. In other words, f of x or y, plug in an x value, it is the original function that gives you the y values or y coordinates. Okay, these are pretty much all the ingredients that we're going to need to sketch a graph. An individual question that we'll be getting to momentarily on sketching a graph is typically going to involve most of these features. We're going to start with a simple one, and then we'll get progressively more complicated through the second and third examples. Now, before we move on, the most important part from information from the first and second derivative are our 4 basic arcs. So again, make sure you are completely comfortable understanding each of these arcs and the dual sign combination, the sine of the first and sine of the second derivative. We're going to calculate the critical points, calculate the possible inflection points, set up our sign chart, and once we have our 2 sign charts, the 4 basic arcs, and thus the shape of the graph should follow. All right, continuing from parts 1 and 2, let's get to example 7, our first example for this lecture, however. And the question is stated very simply: sketch the graph of this function, y equals x to the 4th minus 4x cubed. Now, one option, just plug this into a graphing calculator, and it has sketched the graph. That's not the goal here. The goal that we're going to aim for is using the tools of calculus, basically what we've been covering for the last few lectures, to kind of pull it all together. And it's, in my opinion, a rather kind of beautiful application of calculus, bringing that all together. So if you're feeling adventurous, maybe pause the video and give this first one an attempt. We'll definitely go through this thoroughly before moving on to the last 2 examples. So pause the video and check in momentarily. All right, welcome back. This is a good one to start with since this function is very simple to differentiate. We only need, notice here, the basic power rule. Some of the following examples we get into might require product, quotient, and or chain rules all together, but this one does not. All right, so if we start with our function, let's always keep in mind maybe to consider what our domain is. Since our function, y here, is a polynomial, its domain is just all real numbers. Polynomials are never undefined. They're defined for every real number. All right, we can jump straight to calculating first and second derivatives. Earlier we mentioned if you have no idea what to do for a question, calculate derivatives, first and second derivatives. You'll end up getting a good amount of partial credit doing that. That's a good amount of work usually. And here we're just applying the power rule to get the first and second derivative. Notice each of those derivatives or expressions, we've simplified it by factoring, a common technique that we've done through previous examples in previous lectures. So that should be pretty straightforward. Now that we have simplified our first and second derivatives, it's going to be very easy to find our critical points and possible inflection points. And we should find 2 of each. Critical points come out to be 0 and 3, and the possible inflection points are 0 and 2. Perfectly fine that x equals 0 is both a critical point and possible inflection point. That's not an inconsistency or anything wrong. All right, with those, we can start creating our sign charts for the first and second derivative. You might also want to calculate for each of those x values or coordinates the corresponding y coordinates. And that's just plugging it into the original function, x to the 4th minus 4x cubed. Plugging in 0, 2, and 3, you should get these y values, 0, negative 16, and negative 27. And those are going to be 3 points or ordered pairs that we can plot on our graph once we have some more information. All right, let's go ahead to our sine charts. Again, this should be very straightforward from what we've covered in the previous two parts, creating sine charts for the first and second derivative in parts 1 and 2 of this lecture. And what you should find is for your first derivative, between your critical points 0 and 3, you get 3 intervals, and in order, your signs are negative, negative, positive. Now in that sine chart for the first derivative, notice there is only a change in sign of the first derivative at the critical point x equals 3. And if you take a look at that combination, that change, going from negative to positive, you might recall from the first derivative test, when the sign at a critical point of the first derivative changes from negative to positive, that corresponds to a local minimum. So we know already from this sine chart, x equals 3 in our graph is going to correspond to a local minimum. All right, it should be very similar to create your sine chart for the second derivative. Here we have alternating signs going left to right, positive, negative, then positive. That tells us concavity, if you recall. All right, so that pretty much takes care of the calculus. Some extra features we want to just maybe keep in mind to help us sketch a graph are the x and y intercepts. And we find here that you only get a single y-intercept, but you get 2 x-intercepts, 0, 0, and 4, 0. And perfectly fine for 0, 0, the origin to be simultaneously an x and y-intercept. All right, and if you just finish for consistency, checking or looking for any asymptotes or symmetry, this function, this polynomial, has no asymptotes nor any symmetry. All right, now before we move on to the next slide, make sure you have the sine charts visible. We're going to be referring to them to get our sines on each interval, using our sine charts to get the 4 basic arcs. Okay, so let's go ahead and just set up a basic coordinate system. We're going to use the domain of our function, which so far is all real numbers, so we can consider the graph over the entire x-axis. Some following examples, we might have to modify that. And if you recall from your work before, we had critical points 0 and 3, and possible inflection points 0 and 2. So we basically take all of the critical points and all of the possible inflection points, or all of the endpoints from your sine charts of first and second derivative, and put them all together. And what we have here are 4 different intervals. Now we're going to refer to our sine charts momentarily, but let's use some basic features. We had some ordered pairs that we can plot. We had some intercepts, 0, 0, which we have plotted there as a point at the origin. And we also had our x-intercept 4, 0, plotted all the way to the right there. At 2, or in other words, when x equals 2, the y-coordinate is negative 16. And when x is 3, the y-coordinate is negative 27. Now notice here, I didn't make the y-axis to scale. You could typically go off your page of paper. If you were to draw this accurately to scale, negative 27 would be probably off the bottom of the page. So usually keep the x-axis to scale, but don't worry about the y-axis being to scale. Keep in mind we're just sketching a pretty accurate but rough shape of the graph, not trying to do it in thorough detail, making the x and y-axis both to scale. All right, now this is where it gets tricky. This is going to be where we refer to our sine chart. On each of these 4 intervals, we're going to want to determine the sine of the first and second derivative. So we have 4 intervals here, negative infinity to 0, the interval 0 to 2, the interval 2 to 3, and the interval 3 to infinity. Now you might want to pick an x value in each of those intervals and see in each sine chart where that test point or x value is. If you refer to your two sine charts on each of these four intervals, you should get these four dual sign combinations: negative plus, negative negative, negative positive, and then positive positive. All right, and each of those sign combinations gives us one of the four basic arcs, and we basically have the shape of our graph. It's pretty much connect the dots at this point with these four basic arcs, and if we put them together, passing through those points that we found, we get the shape for our graph using only derivatives. And this is, again, in my opinion, a very nice and beautiful application of calculus, and kind of brings the whole course together. All right, now hopefully this example made sense. Before moving on to the next example, again, make sure you thoroughly understand this first example and all of the individual parts that go into that. So with that in mind, let's move on to the second example. This is example 8 for this 3-part lecture series. And now we're going to sketch a functions graph where the function is no longer a polynomial, but some sort of rational expression or fraction. The big difference with this example compared to the last one is since we now have a fraction, there is the possibility for division by 0. Start off by looking for the domain of this function, and that'll likely guide you through the rest of the problem. One small point to mention: most examples, when we were creating our sine charts for the first and second derivative, most of those functions had domains that were all real numbers. When you create your sine charts for this example, keep in mind the domain of this function, which is not all real numbers. So you'll have to kind of use the domain within the sine charts of first and second derivative. Pause the video, give yourself an attempt at this. You're going to want to use the quotient rule to find the first and second derivatives, which hopefully isn't too much work. We'll check in a few minutes. All right, let's go through this second example on curve sketching. So first thing to mention, this function's domain is not all real numbers. You're going to want to look for where the denominator becomes 0. If you set the denominator x squared minus 1 equal to 0, that gives two solutions, -1 and +1 for x. So what that means is there's two values for x for which this function becomes undefined. So our domain for this function is all real numbers except x equals -1 and x equals +1. All right, just make sure you're comfortable writing that statement, all real numbers except -1 and 1, in interval notation, which corresponds to that 3-part compound interval there. All right, the first and second derivatives are there. They are in fully simplified form. Again, make sure you feel comfortable using the quotient rule. Otherwise, this example could become exceptionally long and time-consuming. All right, so just double check that those derivatives worked out correctly for you. In that second derivative, you should find that there is a factor of x squared minus 1 that has canceled out, which is reflected in that denominator, x squared minus 1 cubed, rather than x squared minus 1 to the 4th, squaring the denominator from the first derivative. A factor canceled out there. All right, now we can move on to finding the critical points and possible inflection points. And this is a peculiar example. This is a function that has no critical points. Keep in mind, what we define as critical points have to be in the domain of the function. And since we're already excluding -1 and +1 from the domain, those don't actually work out to be critical points, even though they give the first derivative becoming undefined. They're not in the domain, so we exclude those. So what we find here is there are no critical points. There's no value for x for which the derivative equals 0. So we have no critical points. There is a single possible inflection point, however. If you set for the second derivative that entire numerator equal to 0, you should find that you get x equal to 0 as a solution. X squared plus 3 equal to 0 has no real number solutions. So we have here no critical points and a single possible inflection point. All right, since we only have one possible inflection point, x equals 0, we just want to figure out the y value, plug that into your original function, and you'll get y equals 0. Now, when we move on to our sine charts, we have to keep our domain for our function in mind, which is all real numbers except -1 and 1. So our sine charts here have to reflect that, our domain, even though -1 and +1 aren't critical points, the domain still splits the x-axis at -1 and +1. All right, same thing happens in the sine chart for the second derivative. 0 was the only possible inflection point, but we have to also consider the domain, which is, again, all real numbers except -1 and 1. So we have two kind of cuts or splittings of the x-axis in the sine chart for the first derivative, and then 3 cuttings or splittings in the sine chart for the second derivative. All right, since we have no critical points, there shouldn't be a change in sign, which we see here for the first derivative. It's all the same sign, all negative. And since we have a possible inflection point, we do get some alternating signs in the second derivative. All right, again, just make sure you're able to correctly get all of these various signs. We're going to want to check the intercepts. You should find that you get a y-intercept of 0, 0, and the x-intercept is the same thing. So we have a single simultaneously x and y-intercept at 0, 0. All right, this one, since it's a rational expression or rational function or fraction, there is the possibility for this function to have horizontal and vertical asymptotes. We can look for vertical asymptotes typically where the denominator becomes 0, which is, again, x equals positive and -1. And to check for horizontal asymptotes, in calculus, we're going to evaluate limits at infinity. And if we do that, take a limit as x approaches positive infinity and a limit as x approaches negative infinity for that function, x divided by x squared minus 1, you should find that you get a horizontal asymptote, which is the limit at infinity of 0. So we find y equals 0 as our horizontal asymptote. All right, the last part, this function does have odd symmetry. It is symmetric through the origin. If you were to plug -x in, that's equal to just putting a negative in front of the whole function. That's going to be a nice check for us to see if there's a simultaneous reflection over the y and x axis. And if we pull this all together, we have to keep in mind our domain, which was all real numbers except -1 and 1. So I drew those there as the vertical asymptotes in red. The vertical lines, x equals -1 and x equals +1. And we had no critical points, but a single possible inflection point of 0. All right, so we basically end up with 4 intervals here. And if you refer to your previous information that we found, we had a single point, which was the x and y intercept, 0, 0. And we also found that this function has a horizontal asymptote of y equals 0. If we use our sine charts to take a look at the dual sine combination of first and second derivative on each of these 4 intervals, we should end up with these 4 sine combinations. And at this point, it's just as simple as putting those 4 basic arcs together with the vertical and horizontal asymptotes, as well as that single point that we know our function passes through, 0, 0. If we put those arcs together on each of those intervals, we should end up with our graph as follows here. All right, let's take a look at our final example. We looked at an example currently, or just before, dealing where the derivatives came from the quotient rule. And just to kind of round out for a nice set of examples, let's take a look at one where you might have to apply, oh, I don't know, product and chain rule. So pause the video, give yourself an attempt at this. We've seen lots of calculations of derivatives involving exponential functions. So hopefully those previous examples through the previous lectures have kind of prepared you for what we're getting to now. So pause the video and we'll check in a few minutes. Welcome back. Let's get to our last and final example for this 3-part lecture series. This function, since it's a combination of a polynomial times an exponential, its domain is all real numbers. So we don't have to make any modifications to our sine charts of first and second derivative, since our domain is all real numbers. Hopefully you feel comfortable applying product and chain rules to find these first and second derivatives. That should be very straightforward compared to the previous examples that we've worked on. All right, and since we have an exponential factor in the function, as like we've always done, we have factored that out after applying the product rule. All right, now that you have fully simplified first and second derivatives, should be very easy to find the critical points and possible inflection points. You get a single critical point, x equals 1, and a single possible inflection point, x equals 2. All right, get in the habit as soon as you figure out an x coordinate of interest, either a critical point, possible inflection point, or something of that nature, figure out the corresponding y coordinate. Let's plug each of those in to the original function. All right, this is a little trickier to compare since exponential values aren't quite as familiar to you. And what you find is at x equals 1, the y value, e to the negative 1, that is bigger than the y coordinate or y value when x is 2. E to the negative 1 is bigger than 2 times e to the negative 2. All right, we can move on to our sine charts for first and second derivatives. Here, they're rather simple since there's only a single critical point and a single possible inflection point. So our sine charts look rather simple. There's only one cutting or splitting of the domain or x-axis. We can move on to the intercepts. And what we find here is that, again, 0, 0 is simultaneously the x and y intercept. All right. You might want to keep in mind basic features of exponential functions. At the far right there is the graph of e to the negative x, which does have a horizontal asymptote of y equals 0. So you should keep in mind, if your function contains an e to the x or e to the negative x, like we have here, x times e to the negative x, and there's likely going to be horizontal asymptotes. There's no vertical asymptotes for this function, but there is a single horizontal asymptote only as x approaches positive infinity. You can get that horizontal asymptote or limit value, 0, by applying L'Hopital's rule. All right, this function has no symmetry. There's no odd or even symmetry. And we basically have all of the information that we need to sketch this graph. All the hard work is done. Now we just have to refer to our sine charts to get the 4 basic arcs. All right, so we basically take the x-axis or domain, negative infinity to infinity, all real numbers. We're going to split that at the single critical point, 1, and the single possible inflection point, x equals 2. So we end up with here 3 different intervals. We had some other information, some ordered pairs and a horizontal asymptote from what we calculated. Notice here, again, I didn't draw the y-axis to scale. I just put the point or ordered pair at x equals 1 above the point or ordered pair at x equals 2. Not worrying too much about exactly how far apart on the y-axis they should be. On each of these 3 intervals, we check the dual sign combination for first and second derivative. And what you should find is you get these 3 sign combinations, plus minus, minus minus, and minus plus. Each of those sign combinations corresponds to one of the 4 basic arcs. And at this point, we just have to connect those 4 basic arcs and have them pass through these ordered pairs, and also respecting the horizontal asymptote only towards positive infinity. If you put all that together, you should end up with this graph, which actually comes out to look pretty good for a sketch by hand. All right, that is our final example. Hopefully you kind of enjoyed seeing how literally the entire mathematics sequence, algebra, pre-calculus, into calculus, calculus 1, kind of all came together. It is rather complicated. It's one of the most complicated topics in a Calc 1 course for most students. But I think you're in good shape for the rest of the course and the rest of the calculus sequence if you feel comfortable with these ideas in parts 1, 2, and 3 of this lecture on derivatives and the shape of a graph.